Okay, so we're going to go through these. Look, this should be pretty straightforward. This is our force diagram, and we draw it from the center of mass, don't we? So let's just draw it from a particular point. Let's just say that's our center of mass. So we have weight. We'll call that W. Which way is thrust?
Forward, left, right.
We'll say thrust is
Forward.
like that. Drag. What can you say if this plane's accelerating to the right? What could you say about the thrust force compared to the drag force?
They will be equal to 0. Or the net force will be equal.
Well, net force would be in the direction of the thrust, wouldn't it? If it was accelerating to the right.
Oh, accelerating.
Yeah. Oh, okay. Okay, so there we go. There's our. Now that should be fairly straightforward. A truck weighing 2,250 kilograms acted by a force. So we know that the net force is equal to mass times acceleration, Newton's second law, and we want to find the acceleration. So the acceleration is equal to F over m, which is 2250, 459, 18. Is it? Oh, yeah. Okay, good. 450 on 2250, which is 1 in 5 is 0.2 meters per second squared. Now, if the truck's originally traveling 11 meters per second, calculate the speed of the truck. Now, we've got to write down what we know. U is equal to 11. V is equal to, we don't know. T is equal to 30. And we know what A is, don't we? A is equal to 0.2. So what did you use, Justin? What formula did you use?
For question A, I went 450 over 2,250. That's what we did.
Yeah, that's right. Forget about that. That's just me being silly.
No, that.
Okay, so what formula did you use for part B?
V is equal to U plus AT.
Good. V is equal to U plus AT. So we've got that our final speed is equal to 11 plus 0.2 times 30. 30 times 0.2 is 6. 6 plus 11 is 17 meters per second. We got that?
Yep.
Good. Yeah, well, you can use a different way. Absolutely. Which way did you do it, Luke? Well, that's just rearranging this, isn't it? That's all you've done there. Now let's think about it. How else do you know the acceleration? Acceleration is the change in velocity over time. Acceleration is the change in velocity over time. And the change in velocity is the final velocity minus the initial velocity over time. But where does this formula actually come from? Well, that formula actually comes from this V equals U plus AT, just transposing it around. Okay, V take away U is equal to AT, and then T is equal to V take U on A, or you can rearrange that to find acceleration. So that's where that comes from. Okay, let's move on to the next one. Tom, what did you do for this question? Question 4.
Worked out the area underneath.
Okay, so the area under a velocity time graph, and considering that velocity is equal to distance over time. If we were to get this time over here, we've got distance is velocity times time. Whenever you're doing that, make sure you look at this. This distance is velocity times time. Now, if this was a square graph, if we had something like this, and this was velocity and this was time, then the area under that would be velocity times time. It's not always a square graph though, is it? Sometimes we have to find an area of a triangle. So between 0.3 and 1, so 0.3 being this here to 1. Now, importantly, we've got to find the area under that whole graph. So let's split it up into two lots. Area 1 and Area 2. So the distance is the area under the graph, and the area under the graph is the area is equal to, I guess, the area of 1 plus the area of 2. Now, considering that 1's a triangle, 1 being a triangle of the length is 0.7, and so it's a half times 0.7, and the height of the triangle is what? What's the height? I guess it's 4.5, 0.45 maybe? Yeah? So we got 0.45 meters per second. And area 2 being a rectangle of 0.7 times 0.3. If we add all that together, what do we get? 3675? Yeah, let's round to 0.37. Yeah, 0.37 I've got. Now, what is the acceleration of the trolley? Well, someone explain to me, how do you find the acceleration of the trolley? Okay, so the acceleration in terms of, let's describe what that means. The acceleration is what of that slope? What is it? What is it of that slope? We've got a slope. Yeah, but the gradient of that slope is the acceleration. You could take any 2 points on that slope, and considering it's a line, it's a straight line, any 2 points on that line is going to give you the gradient. So however you decided to do that is fine. I, for example, might take this point here being exactly 0.1, and I might take this point up here being being 0.6 meters per second. So the acceleration is the gradient of the slope, or rise over run. So I've got that it rises from 0.1 to 0.6. So it rises 0.5 meters per second, and that happens in 0.8 seconds, is it? I think so, yep, that's right. That's 5 over 8. What is the answer? What is it? 0.6. So let's round that off to 0.63. Jason, what can you say about the friction force then? This is a tricky one too. Well, we want to know the friction force. No, so let's think about this. The acceleration of the trolley is 0.63. Now, the trolley has the total mass moving during the experiment was 1.85 kilograms. That's the total mass. Now, the total mass, what can you say about the net force if we found our acceleration is 0.63? What's our net force? Jason? Yeah. What does our net force equal? You don't know? Well, this entire system accelerates. What's the acceleration? No. All right, so we've rounded off to 0.63. We've said that 0.63 meters per second squared, this system accelerates at. We've got that from the graph. What's the total mass? 1.85 kilograms. Newton's second law says that a body will, when a force is provided, will have an acceleration. So our net force is our actual mass of a total system and its acceleration. So it's 1.85 times 0.63. What does that give us? 1.2 newtons. Now that's our net force. That's our net force. Now, yeah, just one sec. What would you say then? So 1.2 newtons. What are the forces in play here, though? Let's think about.
Gravitational force acting on the mass.
Yeah. Mhm.
That'll be 0.2 times 9.8.
Okay. So let's look at the force here. So we've got a cart. We've got a cart, and this is on a table. And oops, this is on a table, and there's a pulley. We're ignoring the friction force on the pulley, though, perhaps. But what's going to happen is, as this goes across and accelerates, there is going to be a friction force opposing the motion, like so. Which way is the net force? Well, then we know that it's going to accelerate in this direction, and it's also going to accelerate. So we've got a 200 gram mass, 200 grams, which is 0.2 kilograms, going in this direction. Now, we know that the net force, let's think about it. The net force is the sum of all forces. The net force is equal to 1.2 newtons. But that is also equal to, let's consider that we've got our weight force down, and the only force opposing that motion is friction. So 1.2 is equal to the weight force being the mass times acceleration of gravity. So 0.2 kilograms times 9.8. Now, we really want to look at this body in this direction. It just makes it a little bit easier to look at it here. Because there's only two forces. There's a force which is pulling to the right, causing an acceleration, and there's a friction force opposing. So 0.2 times 9.8, take away what? Friction. So our friction force, let's rearrange this then. We can rearrange that now. Let's get the friction force over to the left, which means that we have to times 9.8 by 1.2. What does that give us? 1.96. So 1.96. So we've got that the friction force is equal to 1.96 newtons. Oh my God, why does this do this? 1.96, take away, what? 1.2. So our friction force is, I don't know why it does this, 0.7, what the hell? 7, what's happening?
If we got 0.8, would that be correct as well?
Well, we're rounding off to, how many significant figures are we using?
1.156.
It's close enough. Close enough.
Close enough is good enough.
Okay, let's have a look at this question here. What'd you have for 3A, Joe? Yep, we agree with that?
Yeah.
Good. Direction of the velocity in B. It's R. The thing is that the velocity, the ball is still going this way, but it's going this way slower and slower. It's decelerating. Now, that means if it's decelerating, if that means that the acceleration is going up, the net force is up. But remember that the net velocity has nothing to do with force. Force has acceleration, a link to acceleration. But velocity, if it's going down, then the velocity is still down. It's just less down. Less and less and less until eventually the velocity is zero, and that net force, which is up, obviously causes the force, the ball to rebounce back up. But the velocity is still down. Direction of the net force, though, is up. S. And the direction of the net force on the ball at C, well, that's clearly net force is zero if it's at rest. Okay, nice and simple. Now this is where you guys really need to pay attention, because I found a lot of students are really struggling with some of these concepts. A 2 kilogram block. Now, first of all, let's draw our diagram. Importantly, the weight force always acts vertically down. Always. So we've got a weight force of 2G. This is our weight force. And our normal force, importantly, always acts perpendicular to the surface. That meaning that we've got a 90-degree angle, I guess, here. This is our normal reaction force from the ground. And that's why on a slope, you will tend to have an acceleration. The higher the slope, the more acceleration. But of course, that's once we overcome static friction. Now, what I want you guys to do before tomorrow is really have a bit of a look into kinetic and static friction. I'd like you to have a good look into it, how it works. Now, what happens is we have this, when something's moving, already moving, if this is actually on the move, it actually requires less force than to actually get it moving initially. Okay, so what I want you guys to do is tonight, I'd like you to look up kinetic and static friction. Look for some graphs. Kinetic and static friction. Hint, hint. Okay, because you guys will have to do something like that tomorrow. The next thing is, of course, we have this friction. We're going to assume that there's a friction force. Friction is opposing the motion. So there are three forces. Now, according to this, if our component of the weight force going down the hill is more than friction, there will be an acceleration. If it's equal, it means that the net force is zero, and then it'll be either traveling at a constant speed or it'll be stationary. So it says here, find the magnitude of the friction force acting on the block. Zach, what can you say about the net force from the question here? What is it telling us? What is the net force, Zach? 10, yep. Yeah, okay, but what the net force? Think about the net force. What's the question telling us? I want you to read this part. Friction cannot be ignored, but what does it say? 2 kilogram block what? What does it say? Net force is zero. Why is the net force zero? Good. If it's constant speed, it means that there's no acceleration. If there's no acceleration, there's no net force. It's not saying that there's no forces, there's no net force. So to find the magnitude of the frictional force, we have to consider the forces. Let's consider the forces parallel to the slope, though. So we've got a force, guys. Shh. We've got a force going this way, which is, I guess, the component of the weight force. The component of the weight force going down the hill. And then, of course, we've got our frictional force opposing that. Now, let's not really consider the normal force and the force perpendicular to the hill? Because it's not it's not going up or down. It's going down. We're assuming it's going down that ramp at a constant speed. If it's flying off into the air, there's some acceleration up or down, but there's not. So let's only consider the forces parallel to the slope. Parallel to the slope, the net forces is 0. So let's draw our little diagram. If I was to, this angle is 30 degrees. That means that this angle here is also 30 degrees. So let's draw that triangle. We've got a triangle, we've got 30. This here is our weight force, which is, well, I guess, it's actually, that's wrong, isn't it? Our triangle actually looks like this. This is 30. This is our weight force. And which one are we trying to find? Are we trying to find this thing here or this thing here? We're trying to find the bottom one. Now we're going to call that F, force in the X direction. Well, that's fine as long as you defined it. So from that triangle, you can say that the sine of 30 is equal to the force of X over the weight force. And our weight force is 2G. 2 times 9.8. Which means that our force in the X direction is equal to 2G, which is 19.6. 2 times 9.8. 19.6 sine of 30. What does that work out to be? 9.8?
That equals 9.8.
Good. Because sine of 30 is a half. Okay, so we've found what our force in the X direction is. Now, our net force is our force in the X direction, looking at this diagram here. Our force in the X direction, take away the friction force. So, 0 is equal to our force in the X direction, take away our friction force. If we rearrange, that means we get the friction force on the left. So we've got our friction force is actually equal to the component, X component of the weight force, which we've already found, isn't it? We've just found that, which is 9.8. So the answer is 9.8 newtons.
Well, it is, but it's not from it's going down. It's equal to gravity, so it's not.
That's because it's traveling at a constant speed. The net force is 0, which means the frictional force and the component of the weight are the same. That's not always going to be the case, though. Let's think about when tomorrow we're going to be looking at the critical angle. We're going to raise a I guess a slope, and we're going to work out in time using a timer. We're going to time the time it takes and work out the acceleration from there. Now, what's going to happen, though, do you think, if that we've got a 1 kilogram mass, a 2 kilogram mass, and a 3 kilogram mass? What's going to happen if you have a 1 kilogram mass compared to a 3 kilogram mass, do you think? Sorry? Yes, good. So the critical angle is going to change depending on the mass. What about the acceleration? If I have two things moving, but one is a mass of 3 kilograms compared to 1 kilogram, what's going to have a higher acceleration, do you think? I don't know. Let's find out. You'll find out tomorrow. If you think about it, same force, if we have more mass, you'd probably assume less acceleration, wouldn't you? All right, let's have a look at this question anyway. We'll get to that later. All right, a 10 kilogram box. Now, we're going to assume that it's 150 newtons. So this is actually technically wrong. This is 150. Okay, once again, you just need practice with these questions. It's being pulled by a constant speed. What can you say about the net force, Lockie? Yeah. What's the net force? Good, thank you. Why is that? Thank you. Constant speed? Constant speed means no acceleration. No acceleration, no force. Good. Okay, so we know that the net force is 0, but let's consider what's happening. Which way is the motion? This box is being pulled in this direction. I'm telling you now, the box isn't being lifted up into this direction. It's being pulled at a constant speed. So we've made an assumption that it's pulled across the floor. But the tension force, if you think about it, if you're holding a rope, the rope isn't necessarily in this direction. The rope is actually held at an angle. And that angle being, in this case, 50 degrees. So what we need to consider here is that considering that the force is actually in this direction, I guess really there is actually a contact force, here and here. These are sort of equal and opposite. Okay, so I guess they effectively cancel each other out. But what isn't being cancelled out is this component of this force here. Now, really, what would we call this force? We call this, I guess we could call it tension. In which direction? X or Y? X. Where do I draw friction? What do I do there? Okay, good. So that's going to be in this direction. So they're the only two forces we're considering. We're not considering the tension. We're considering the tension in the X direction. So if we draw our triangle again, this triangle being a little bit easier because it's not on a slope. 50 tension in the X direction, and we've got 150 newtons. So if we've got 150, so that means that the tension in the X direction, or cos of 50, is tension in the X direction over 150. So the tension in the X direction is 150 cos 50. So let's consider the right being positive, left being negative. Makes sense, wouldn't it? Therefore, the net forces is the tension in the X direction, which is 150 cos 50, take away friction, and that equals 0, doesn't it? So rearranging, it's the same question as before. The friction force is equal to 150 cos 50. What does that equal? 96.42. Now, considering that what you do here, remember significant figures. This is just giving us no decimals, all right? So let's just round off to the nearest whole number. What have you got? 96.42. So let's just round off to 96 newtons. Okay, so let's have a look at this diagram. We've got a weight force, we've got a normal force, and Newton's third law says that for every action there's an equal and opposite reaction. This is in terms of contact forces. So what can you say about this normal force? We're asking to find the normal reaction force now. Now, let's try prove it mathematically. The net force in the y direction is equal to 0 also. There's no acceleration up or down. And the two forces that we're considering are... Now, we're looking about the center of mass here, though. All right? There's actually, at this point here, we're not considering that because there's actually an equal and opposite reaction force there. So don't worry about this point here. We're actually worrying about the center of mass. The two forces at the center of mass is weight and the normal reaction force, and they equal 0. So if we were to take a normal reaction force, take away the weight, that equals 0. So our normal force is actually the weight force. And weight is equal to mg, which is 10 times g, which is 98 newtons? 98 newtons. All right. More of these questions. Let's have a look. Jimmy parks his car on a hill. The car has a mass of 750. What is the weight of the car? Lewis, what do you have for that? Well, let's look at it. Let's try it. What is the weight of the car? Well, its mass is 750 kilograms. What's weight though? Weight is a force. So, okay, good. So 750 times 9.8, which is, what's that? 7,350 newtons. Okay, so this car weighs 7,350 newtons. And what is the component of the weight acting parallel to the road surface? Well, let's draw our diagram. We've got W here, and our normal force is perpendicular. So that means that we've got much the same question though, isn't it? You see that these questions are very repetitive. You'd know you're going to get these questions in an exam. You're going to get these questions in a SAC. So we've got an angle here, which is 20 degrees. So if we were to draw that triangle again, this being our weight force, this being theta, which is 20 degrees, and we want parallel to the road surface. So I guess we've got this triangle down here, but it's sort of been turned on its head. So this, the component that we're looking at is a force this direction. We'll call it Fx. So what's that, Lewis? We're using sine or cosine, do you think? Sine. So we've got sine 20 is equal to Fx over its weight force. Weight force is 7,350, isn't it? So Fx is equal to 7,350 sine of 20. What is that? What do we get for that? Somebody? 2,500. Now, significant figures, none of us, thank you. A lot of you are still writing 4 to 6 decimal places. You don't need to, because if you think about the question, what is the most accurate part of that question? There is nothing that gives you any decimal points whatsoever. So in your answer, you do not need any decimal points. You can round up or down. Which of the following best describes, what do you have for this one, Chris? Friction force between the tyres and road? Absolutely. The reason why the other ones, handbrake and the wheels, friction is a contact force. So between the wheels and the brakes, no. Reaction force on the road, perpendicular, whatever, no. B. Let's have a look at this. A sudden oil spill higher up the road reduces the roughness of the road surface and the car starts sliding down the hill. What is the net force on the car? Okay, now let's have a look. The car has a mass of what? 750 kilograms? And the acceleration is 0.26. So our net force down the hill is 750 times 0.26. What is that, guys? 195? Okay, 195 newtons. So the net force on the car is just 195 newtons. Down the hill. Is there another question? That's it. Well, that's pretty.
Question 16. I did not understand it.
Okay, now a car accelerates away from the lights. Engine provides a constant driving force on the wheels. At first, the car accelerates at 2 meters per second squared, but as it speeds up, the acceleration slowly drops to 0. Suggest a reason why acceleration drops to 0. Adrian, what have you got for that one?
Is it because it went up a hill? I tried to keep going.
No, this is a different question. All right, what can you say? If a car accelerates and is getting faster and faster, what can you say about the resistance? Air resistance, maybe. Good. So you could. So one thing. Yep. What's that?
It reaches a constant speed. That's why the acceleration drops to 0.
Well,
The net force
That's right.
That force is zero. The acceleration must be zero.
So as you increase the speed, as you increase your speed,
Acceleration decreases.
increase the speed, you're also, the air resistance is increasing. Air resistance is increasing. And that would be one thing. Any other reasons? Okay, so I can think of two things. Friction on the road eventually balancing out that driving force, and also increased air resistance balancing out that driving force. I would, if you were to verbalise those, that would be fine. What about this one, guys? A runner. If you think about it, if we look at his shoe, sort of, you know, shoe, ground, this is, I guess, they're actually pushing up at an angle. And what happens is, let's just say this is the ground. You're actually pushing the ground at an angle, and the ground is pushing you. So what law is that referring to? Newton's third law. So Newton's third law actually refers to, a runner is pushing down on the ground. I won't write this down, but a runner's pushing down the ground. The ground is then pushing back. What about this one? This is a pretty much a simple equation as a motion question. What did you do here, Jacob? Question this one here.
I did
Sorry?
Is that right?
Yeah, explain.
I did the formula where it's half a times t squared equals x.
Okay, so what formula did that come from?
From the one where it's u plus t.
Okay, good. Ut plus a half at squared, that one?
Yeah, but because u 0.
Shoot. What's happening? Ut plus a half. What's going on? You do, don't you? It's been dropped. Now, considering that it's dropped, the initial speed 0, that means that this section here is obviously 0. So that means that x is a half at squared, and a being 9.8. Oops. Half at squared. So a half at squared is half times 9.8, 4.9, times 1.6 squared. 1.6 times 1.6. What is that? 16.6. I don't know. Tell me, guys. I can't be bothered thinking today. What is it? 2.56 times 4.9? What have we got? What's the answer? It's about like 13 metres or something?
It's like 12.5.
12.5 metres? Good. So if you got around about 12.5 metres, you're correct. That was just an equations of motion one.
How long would it take though for the sound to get up the well?
Sorry?
Speed of sound?
Well, speed of sound is about 340 metres per second.
So how would you put that into the equation?
Yeah, but we're assuming that we're ignoring the time the sound takes.
No, but if we had to implement it,
What about it?
how would we measure it then? We'd have to minus.
Velocity equals distance over time.
Because it says you should ignore the time the sound takes.
Well, you'd have to then add the time it takes to get up. You'd have, this is 340 metres per second.
Yeah.
And the distance you know. Yeah? And from there you could work out the time. Alrighty. Lucy drags a box. Now, guys, this is exactly the same as before, isn't it? I expect you guys to be able to finish those off, and if you can't get that question, then you're going to have some problems. We've just been through probably three of that type. Exactly the same thing, normal reaction force. Now, I'm telling you now, these have come from various Year 11 exams. So you can see there that a lot of these questions, they really do tend to repeat themselves. There's only so many ways they can ask you. This one's an energy one. I'll leave that for today because I guess we're looking at Newton's laws. But I did want you to have a go at those. I'm not going to go through any more. I'll stop there. Are there any questions before I stop this video? Any sort of questions we're having so far? All right, I'm going to stop there.